Thanks, Tilman. Thanks, everyone, for coming. Thanks for the introduction. Yeah, as Tilman said, I will be talking about an ongoing revolution to weather prediction. And yeah, maybe I'll be answer to some question, probably not all, that you may have. So, as of today, whenever you consume a weather forecast via your favorite app or a newspaper or weather website, then these are typically based on physics-based models of the atmosphere. So I'm not sure if I can hide this here somehow. Yeah, okay. Okay, so weather forecasts today are based on physical models of the atmosphere, where systems of partial differential equations are used to model atmospheric processes. And those models, they are run on supercomputers by weather services, and these differential equations are solved on three-dimensional grids around the world. You can see an illustration here on the left-hand side, and these grid cells are something like 10 by 10 kilometers in size for the highest resolution models available today. Now, how this looks like in practice is that given a best estimate of the initial state of the atmosphere, initial conditions at some time, we can then use the physical laws modeled via systems of partial differential equations to make a prediction for the next time step, or for the state of the weather in the next time step, which we can then again use as an input to these equations and get the next prediction at the next time step. So in this process, however, there were lots of uncertainties. Most importantly, maybe uncertainties about the initial conditions, because of course we do not observe the weather everywhere on this three-dimensional grid. And then there are also uncertainties about the models, because lots of the processes in the atmosphere cannot be resolved in the current grid resolutions of the models. So they have to be put into the model indirectly. For example, processes, chemical processes in clouds or radiation processes. Which is why nowadays, most weather services don't run just a single model, but they produce what is called an ensemble forecast. So same model or a slightly varied model is run multiple times, starting from different initial conditions. And then over time, different potential scenarios for the future development of the weather develop. And from those, we can estimate the uncertainty and, for example, compute probabilistic forecasts, such as here the probability of precipitation over the UK. Now, these type of models, these numerical weather prediction models, have been used in day-to-day weather forecasting for about 70 years. And this story of weather forecasting is a maybe sometimes unnoticed success story. So that's why it's called here a quiet success story. I'll talk about the success story part first, and then why it's a quiet story. So what you can see here is a summary measure of forecast skill for forecasts by the ECMWF, which I mentioned already, the European Center for Medium-Range Weather Forecasting, which is arguably one of the most advanced forecasting centers in the world. And what you can see here is the ACC, which is the anomaly correlation coefficient for one meteorological variable, averaged over a year in a running window. So here, higher values indicate better forecasts. And what you can see here is the forecast quality plotted against the time. And you can see all lines go up. So essentially, forecasts get better and better over time. Different colors here correspond to different lead times. So yellow lines are forecasts that were made 10 days before, and then from green to blue, it's 7, 5, and 3 days. But if you want to know more details about how much weather forecasts get better, we can, for example, look here at this green line you can see here. So in the year 2020, and then we can draw a horizontal line to the left from here, and we can see when we meet this red line. And this is around the year 2000 approximately. So meaning that 7-day ahead forecasts in 2020 were as good as 5-day ahead forecasts in the year 2000. So that's sort of a rule of thumb about the improvement of weather forecasting, is that in every decade, we gain about 1 day of forecast lead time to have skillful forecasts. Now, this success story is often called a quiet success story or a quiet revolution here, borrowed from this paper by Peter Bauer and colleagues. And they argue that this success of weather prediction has often gone unnoticed, because there have not been any single fundamental breakthroughs in these past 70 years, but weather forecasts have gotten better and better due to a steady accumulation of scientific knowledge and of advances in technology. However, as I argue, the impacts of these improvements are still among the greatest of any area of physical science. However, now this quiet success story may be facing a rapid and unprecedented disruption. And the reason for this, as you may have guessed, is AI. Because over the past years, AI-based data-driven weather forecasting has arisen as a new paradigm. So principle, with all the hype around AI and the use of AI in lots of different scientific disciplines, of course, also people interested in weather forecasting were wondering whether we actually need all this physics. So can't we just try to model getting from one weather state to the next weather state by a complicated machine learning model, for example, a neural network. So instead of using these partial differential equation models to get from one time step to the next, we could just learn how to do this using a machine learning model, because now there is a sufficient amount of past data available. So the first benefit of this might, of course, be better forecasts. So maybe we can actually do this better than using physical models. Or at the very least, we are not better overall. Maybe we can get better at different timescales or locations where we know that the physical models have little or no skill. Or if we don't get better, but sort of reasonable forecast out of this, one main advantage will certainly be that this could be done much faster. So instead of having to solve differential equations on a supercomputer, this is just one forward pass through an arguably complicated neural network, but this is something you can do on a laptop. So at the very least, we get much lower computational costs out of this once we have trained such a model. Now, at this point, I would like to ask you what you think. So as of today, can AI-based weather models outperform physics-based weather models? We can do this via a quick show of hands, maybe. So who still believes in physics and that physics-based weather models give the better forecast? Okay, who believes in AI models? Okay, so it's split pretty much 50-50, and it's very interesting to ask this question to different audiences. So the answer is maybe. So it's not really a decisive answer, I know. Maybe I should have put probably instead, and I'll explain why in the next minutes. Before I do this, I would like to start, though, with a short history, but history here starts 6 years ago, approximately, because this was when the first papers appeared of people who tried to actually do this, so try to really implement neural network models for weather forecasting. At the very beginning, this was nothing more than a general proof of concept. These models were only comparable to very simple toy models of the atmosphere using physics-based models. And then there was incremental progress. The models did get a little bit better, but they always remained very far behind any sort of operational model that has been used in day-to-day weather forecasting. So 3 years ago, there was a broad consensus that it would seem unlikely that these AI-based models would be able to challenge really operational physics-based models. And many popular meteorologists went on the record and wrote in their papers that this is not going to happen in the next decades. It turned out they were wrong. And just 1 year later, so over the past 2 years, there have been some unprecedented and to many surprising developments. So what happened is that in a short span of time, starting here February 2 years ago, and then continued over time, different models were being proposed, so different AI models for weather forecasting. ForecastNet model, Pengu weather model, GraphCast model, and this development has essentially continued. So my list here stops at some point in summer last year, but every couple of weeks, essentially, there's now a new group, a new paper coming out where there's a little improvement to these current state-of-the-art weather models. Now, when you look at these papers, you will immediately see two things. So one is that they are written typically by large groups of people. And second, that most of these people do not come from universities, but they come from tech companies like NVIDIA, Huawei, Google, DeepMind, Microsoft. So this potential revolution in weather forecasting has also made it into public news articles. So here I just brought a few examples from last year, July, which were in the days after this Pengu weather paper had been accepted in Nature. And you can see that even the Tagesschau was reporting on AI in weather prediction. Now, what all these models have in common is that they reach, at the very least, or surpass, in many cases, the forecasting performance of state-of-the-art physics-based weather models that are being used in day-to-day weather forecasting by weather services. So they provide accurate forecasts overall on average, but also of individual events like tropical cyclones, heat waves, and so on. And as expected, producing forecasts is of orders of magnitude faster and cheaper than with physics-based models. For the results, I brought you two examples from these Pengu weather papers. So here is the RMSE, so a measure of forecast error for two meteorological variables. And lower values here indicate better forecasts. Red is the AI model, Pengu weather. Blue is the IFS model, which is the physics-based model of the European Center for Medium Range Weather Forecasting. So lower values are better forecasts. So you can see that the red line indicates that the Pengu weather model is better at predicting these two variables on average. And the second example that also comes from the paper is on tropical cyclone forecasting. So these are two tropical cyclones. And the red line is the AI model forecast, the blue line is the physics-based model forecast, and the black line is the true cyclone track that was observed eventually. And you can see why the physics-based model does make some quite drastic errors here. The AI model's forecasts almost look too good to be true and seem to match the true cyclone track almost perfectly. So over the past year, code has also become available to at least run these models. So there is no really open source code to be able to train the model yourself, but at least you can use the estimated models to make forecasts. And that's something that we do at KIT. There is this KIT weather webpage that you can take a look at if you're interested in this. So what we are doing, we are running this Pengu weather model quasi-operationally every day, and we start this from initial conditions from the physical model of the German Weather Service. So you can see two forecasts here. Left-hand side is the AI weather model forecast started from the initial conditions of the physics-based model forecast. And on the right-hand side is the corresponding physics-based forecast of the German Weather Service. So here, these are forecasts that were initialized on Friday last week when I made these slides, and that should be valid approximately now. And you can see that they look fairly similar. So there's a bit more fine-scale detail in the physics-based model forecast, but the overall picture does look very similar. And what these experiments allow us to do is that we can actually compute how much it costs to produce these forecasts. So here I've computed the costs for producing 1 year of forecasts. I've assumed that, well, you have a supercomputer in your basement, as we have at KIT, and you just have to pay for electricity, and that you are producing forecasts as the German Weather Service does this. So 2 model runs per day, 40 ensemble members every day for 1 year. Now, when you do this with a physics-based model, as the German Weather Service does, then this causes electricity costs of around 440,000 euros, which is pretty much the average price of a single family home in the US. And that's what an AI image generation model thinks such a house would look like. Now, as you might imagine, I already told you, AI-based weather models are able to do this much cheaper. So you can have a guess for yourself if you want, but this actually would cost 200 euros. So this would be if you use the Pengu weather model. You also get a house for this. The downside is that it's made of Lego bricks only. This is, of course, only for producing forecasts. What's missing is the model training. And that's a bit of the caveat here is that we cannot really verify this number because there is no code to train this model. So we have to trust the authors, what they write in their paper. But if you believe the authors, then this training would cost around 10,000 euros. So a lot more than producing 1 year of forecast, but still magnitudes less than running a physics-based model. So thus far, I've mainly talked about work that other people did. So in the last few minutes, I would like to talk a little bit about our work. So one question that we are particularly interested in is how to do all of this probabilistically. So most of the efforts that you have seen before have been focused on deterministic forecasts. So just one model run of the AI model, making one deterministic point-valued forecast. However, this makes it impossible to quantify forecast uncertainties, which is very important in different applications. So the question we are interested in is how do we quantify uncertainty from these data-driven weather models? And one way of doing this would be to have inherently probabilistic models, for example, generative machine learning models. And there have been the first few models that go into this direction, but still the majority is still deterministic models. So we consider mainly 2 approaches, getting from deterministic to probabilistic forecast. And one is using an ensemble of initial conditions to generate an ensemble of forecasts by running the data-driven model forward from these different starting conditions. And these could be generated, for example, by taking the best guess initial conditions, adding some random noise to this, or using the initial conditions of a physics-based ensemble model, or generating initial conditions from past data. So the second approach of doing this is to not run the model multiple times, but just take a data set of past forecasts from the deterministic model and corresponding observations, and then learn in a second step how to equip this with uncertainty information. So how to best generate a probabilistic forecast from these deterministic predictions. And there we looked at 2 ways of doing this, one more statistics-based approach and one more machine learning-based approach using neural networks. And I just want to show one slide of results here to indicate how those results can look like. This is, again, the measure of forecast error via some error metric, the CRPS, which measures the quality of a probabilistic forecast. So here again, lower values indicate better forecast. And forecast quality here is shown as a function of forecast lead time in hours. And you can see different lines. So this red brownish line is the operational model by the ECWF. And then these blue lines are different initial condition-based approaches. And these yellow, orange lines are these post-hoc uncertainty quantification methods. And you can see that we actually can get improvements over these state-of-the-art physical model for something like up to 5 days lead times, specifically when we use these post-hoc uncertainty quantification methods. So with this, I'd like to summarize. And hopefully, I have been able to demonstrate that there have been surprising and tremendous amounts of progress in AI-based weather forecasting over the past 2 years alone. And this is likely an unprecedented disruption in this quiet revolution of weather prediction, which may, likely will, profoundly influence the way weather forecasting is done in the next decades. As you have seen, these AI models, they provide very good forecast skill, and I believe that they are here to stay. But to be fair, one has to state that they can't really replace the physical models yet for end-to-end weather forecasting tasks. Reason for this are a little bit more complicated, but essentially to generate these initial conditions on a three-dimensional grid, for this process, you would still use the physical model to collect all different kinds of information and then generate this gridded data set. There has been rapid progress, but I think there also are many open questions. For example, how to quantify forecast uncertainties, as I've just shown you, but also whether these models will continue to work in a changing climate, because they have been trained on data from the past 40 years, but weather and climate may change in the next decades. So it's maybe questionable whether these models will or will not work in the future. And then maybe as a more general perspective, as you have seen, many of these developments are not driven by university research, but are driven by private industry. With the code not being open source, you are not able to train the models, adapt the models. So this obviously leads to the question, where does this leave us as university researchers? And I believe that there's ample need to really improve our understanding about the capabilities, but also the limitations of these approaches from a research perspective. And this also, of course, extends to weather services, which are now wondering what they should be doing. So, of course, there's also lots of interest in using these data-driven models in operational forecasting, and their first experiments and running these models really on a day-to-day basis at the weather services. So with this, thank you for your attention, and I'm happy to answer questions and discuss.